So welcome everyone to today's seminar. Today we have Renske Smit, who's going to tell us about the cold side of galaxy formation at the cosmic dawn. I have no idea what this noise is. It stopped. Okay, good. So she did her PhD in Leiden in the Netherlands and graduated in 2014 using HST and Spitzer data to study star-forming galaxies at the cosmic dawn. Then her work received the European Astronomical Society Merit Best Thesis Prize in Observational Astrophysics. Then she moved to the UK, first for 2 years in Durham, and then for 3 years in Cambridge on a Rubicon and then a Newton Kavli Fellowship, studying the same galaxies, but mainly with ALMA. Then she joined the JWST near-spec GTO team to prepare for the evolution to the revolution of data that James Webb would bring for the study of the early universe. She was then awarded an STFC Ernest Rutherford Fellowship to further study galaxies in the early universe with JWST and ALMA, which she took to the Liverpool John Moores University, where she was made a reader, equivalent to associate professor in 2022. Thank you so much, Renske, for accepting our invitation. You may start when you're ready.
Okay. Thank you, Anna. Thank you for the introduction, and thank you for the invitation. I wish one day I can join I can visit in person, but not for now. So yeah, today I want to talk about, I made my title The Cold Side of Galaxy Formation at the Cosmic Dawn. The cold side mainly refers to the fact that I use a lot of ALMA in a time when most of my field is very dominated by JWST. But really I'm using also some hot gas tracers from ALMA. So really what I think the theme of today's talk will be is about how rapid galaxies can build up in the very early universe. Okay. So let's talk a little bit about, the big picture of the very early universe. So what we know for a fact is that 400,000 years after the Big Bang, recombination happens, and recombination leaves behind a dark and completely neutral universe. And then a few 100 million years later, the first stars form, so-called population 3 stars. They are thought to be very massive and explode on very short timescales. And as they explode, they enrich the gas around them with heavy metals. And these metals help to cool the gas. And so the next generation of star formation happens pretty quickly and forms the first galaxies. And as these galaxies start growing, they start producing the ionizing photons, we think, to reionize the universe. And this process of reionization is complete at about 1 billion years after the Big Bang, and that corresponds roughly to a redshift of 6. And so this first billion year, redshift 6 and higher, is sometimes referred to as the cosmic dawn, because of how all these first milestones for stars, metals, and reionization happen all in this early epoch. And we have a number of big questions. How early do the first stars form? How do galaxies evolve in the first billion years of cosmic time? And what sources reionize the universe? But today, I think the focus of my talk will mainly be about the second question. How do galaxies evolve in the first billion years? And so the way we study these galaxies is by looking very deep into the universe, and seeing galaxies that, as they were roughly 13 billion years ago. And what we need to sort of understand about when we look back in time, how different the entire universe looks. And it's maybe best represented with this cosmological simulation, 2 snapshots at redshift 0 and at redshift 5 of the same volume, co-moving volume of the universe. And what you're looking at is the gas density of the universe. And what you see at the low redshift universe, at redshift 0, you see these high contrasts, these big voids and big overdensities. Whereas at high redshift, first of all, there's still gas everywhere. The halos aren't that big yet. They still need to grow and evolve. So we have many smaller galaxies that are still very rapidly merging, but also the gas is still very much falling onto these first halos. And so the specific accretion rate of gas is extremely high in these early galaxies. And if we assume that gas converts into stars at the same rate at high redshift as it does at low redshift, it means that the specific star formation rate, so the doubling time of galaxies, is very, very high, almost 2 orders of magnitude higher at these high redshifts than what we see in the local universe. And that changes everything about how galaxies look and how star formation takes place. So how do we observe galaxies? How do we find these distant galaxies? It's a bit like looking at a needle in a haystack. So this is a nice simulation from when it was still done with the Hubble Space Telescope, looking at different filters from B band to the H band. And you can see as you go to higher redshift, we're looking at very much the UV part of the spectrum. There's a strong break, the Lyman break, between 912 and 1216 angstrom. And that causes a very clear dropout signature as these galaxies go to higher and higher redshifts, right? And so based on where these galaxies, which bands they drop out, we can look at more and more distant galaxies. While this was only possible out to redshift 11 or so with JWST, James Webb has been able to extend this quite significantly. So when we find these galaxies, we can count them. We can convert that UV luminosity that we used to see with JWST into a star formation rate using maybe the colors as an estimate of the dust correction that you need to apply. And then you can construct so-called star formation rate functions, which is what you see here, and it gives an indication of how fast galaxies build up. So we just have number densities here at the y-axis as a function of star formation rates, and what used to be from redshift 8 to redshift 4 is almost 1 billion years in cosmic time. You can see at a fixed star formation rate, the number density of galaxies just in 1 billion years increases very, very rapidly. Right, so the numbers of galaxies increase rapidly. And now, of course, we're looking at this with JWST and ALMA. JWST can look at a huge dynamic range of galaxies. In fact, most studies have been done at the very faint end. But with ALMA, we're also looking at ALMA is less sensitive, so we're mainly looking at galaxies sort of around the knee in this star formation rates or luminosity function. So sort of the brighter galaxies. So that's just for context. And what do we know? Prior to JWST and ALMA, what did we know about these galaxies, right? We had very little information. First of all, we had from JWST sort of an indication of the morphology. Most galaxies just looked compact and not particularly interesting. And then we were able to look at the color of the UV slope. So that's shown here, that we parameterize that as beta. It's not particularly relevant. Blue galaxies are here, galaxies are up there. And if we look at a beta of -3, that's sort of a maximally young, completely metal-poor, completely dust-free galaxy. And as you can see, this is a compilation, a review of various measurements. Most galaxies are very close to that sort of extremely blue limit. So most galaxies are very blue and were thought to be, because of that, very primordial, not very evolved. And so what I want to talk about is how in the last few years, with both ALMA and JWST, this picture has started to change, and there started to be evidence for very early maturity in galaxies in the first billion years. And I'll look at that in 3 different ways. First, I want to talk a bit about how there's too many very bright galaxies above redshift 10. This has been a very high profile, it's still ongoing, but a very big puzzle, and a lot of research efforts are going towards this, so I'm trying to understand this. And then I want to talk about dust and how dust forms and how quickly that can form, and why it's so interesting to look at high redshifts and what we learn about dust formation. And then I want to talk a bit about kinematics and talk about how early can the first disks already form. Okay, so let's start with galaxies above redshift 10. So earlier this year, there was a new redshift record. That was very exciting. The most distant galaxy in the universe is now at redshift 14.2. It's a huge jump. And with this paper, this figure came out. And it sort of summarizes for me why it's so surprising to find these type of galaxies, some of these galaxies, right? So we're looking at all the blue points are galaxies that were identified over one field of view. We're at 2 fields, Goods North and Goods South. Blue points are photometrically selected galaxies, and then red points are galaxies that were spectroscopically confirmed. And I wanted to draw your attention to this dashed line here, which indicates how luminosity would evolve if the luminosity as a function of halo mass, that ratio would stay constant, right? So evolution that follows the halo mass function, halo mass evolution, are these dashed lines. Right, and so at redshift 8, we said that there's very few galaxies around this line. So galaxies brighter than -21 in UV, rest frame UV luminosity are very rare. And so we expect naively, if galaxies roughly follow halo mass evolution, that by the time you get to redshift 14, that there should be very few galaxies brighter than UV magnitude of -19, right? And that isn't true. Like you can already see there's a lot of blue points here that sort of start to exceed this dashed line, which you wouldn't expect. Why do galaxies suddenly at these very high redshifts show up and so bright? And then these two circled galaxies were spectroscopically, very convincingly spectroscopically confirmed. And they're much brighter than anything that you see at redshift 8. There's no equivalent of these galaxies at lower redshifts. So this isn't the first time these kind of galaxies have been seen, right? There's a number of other galaxies. The first galaxy that was very famous was GNZ11. And now with GNZ11, you could argue maybe there's a clear explanation of why it could be so bright. So what is so iconic about GNZ11 is that it has many emission lines in its spectrum and many high ionization emission lines. So carbon-4, nitrogen-4, helium-2, they all need a very hard spectrum. So that could be from an AGN, for example, or it could be sort of extreme starburst. Many people have pointed out how the high N over O abundances match that of globular clusters in the local universe. And so maybe there's a link there. Maybe there's, massive globular clusters forming here in some kind of burst. It's still unclear why there's no equivalent of GNZ11 then slightly lower redshifts, but this galaxy is very compact, which fits with both the AGN or starburst scenario. So, maybe there's some explanation here, right? But what's so surprising about this new galaxy, redshift, so GSC14, this really bright one, is that we find the opposite. We find no evidence for these bright emission lines, right? So there's no evidence for an AGN or a particular intense starburst at all in this spectrum. I just emphasize that a little bit more. This galaxy also seems to be a bit more extended compared to two N emitters, GNZ11, GHC2. They're indicated here with orange and green points. This galaxy, the surface brightness is just a bit more extended than what we've seen so far. So this galaxy seems to be fundamentally different, and you can't just explain it with some exotic scenario. Now, this galaxy, unfortunately for GNZ11, we have some emission lines in the rest frame optical still, which helps us to learn a lot more about the galaxy. But that's redshift 10.6, this is redshift 14, and all the rest frame optical lines have moved out of the near spec wavelength range. So anyway, we can see these lines potentially with MIRI, but it's extremely expensive. So how to make progress? So just to sort of see what are the, how does observing emission lines change from redshift 0 to redshift 14. I'm just showing here a spectral energy distribution of what might be a typical galaxy at redshift 7, but placed at redshift 0. So obviously at redshift 0, on the background, I'm showing the transmission through the atmosphere. So in the optical window, there's these many lines, O2 or 3H alpha, that can teach us a lot about the properties of these galaxies, and they're very easily accessible. But if we then move to redshift 7, you can see that all these lines have moved into the mid-infrared. They're not observable from the ground anymore. So you need, for example, near spec, but near spec can observe them really efficiently. The only line that you can potentially see from the ground, the rest frame view is the Lyman alpha line. But we're also entering the epoch of ionisation. So there's a lot of neutral hydrogen in the intergalactic medium, and so Lyman alpha gets scattered away. So all of these, so from the ground, things get a lot harder. Fortunately, at the other end of the spectrum, can you still see my slides? Yeah. there's the sub-millimeter window where ALMA observes, and some of the brighter lines in the far infrared starting to get accessible at high redshift. And it becomes even better at redshift 14. These first frame optical lines need to be observed in MIRI, but actually ALMA in some ways becomes more efficient than even JWST observing emission lines because of how nicely some of the brightest lines in the entire SED spectrum of galaxies moves into this excellent window. Right, and so very bravely, a PhD student that I'm co-supervising in Leiden decided to submit a DDT program to try and scan the redshift range for this source for the so-called O3 line at 88 micron, right? And so this is what that scan looked like. And indeed, he was successful in detecting oxygen at a redshift of 14.18. So this is the most distant emission line ever observed. It's nicely detected the redshift 6.6. It's very nicely centered on the central galaxy that we're looking for. This is a foreground source, by the way, next to it. This is the galaxy. And it's very interesting to think about what does that mean? You can already see oxygen at redshift 14. Like there needs to be a reasonable amount of enrichment already at such an early epoch. So we explored that a little with my PhD student, Catherine Ormerod at LJMU, and the way we derive or try to constrain oxygen abundance by looking at the luminosity of the O3 line over the star formation rate in the galaxy. And there's a large degeneracy with ionization parameters, but exploring a wide range of cloudy models with different densities and different ionization parameters, we can exclude pretty much that these purple lines, which are 5% solar oxygen abundance, and we need at least 10% or more solar oxygen abundance. So we have a sort of a nice lower limit of how enriched this galaxy already needs to be. And that's from everything that we've so far talked to modelers about. This is really difficult to understand. How can a galaxy at redshift 14 not only be this bright, but already be that enriched? 10% solar is quite a lot compared to simulations of these galaxies. So this is truly a new challenge for galaxy formation models. So let me move on to my second topic about dust and why is it so interesting to study dust in the very early universe. So, best instrument, of course, to observe dust directly is ALMA, and the large program that arguably collected the most detections of both cold gas and dust was the Rebels large program. It was cycle 7, I believe. As, where we looked for galaxies that in many ways could be similar in their luminosity to this redshift 14 galaxy if we evolved it according to the halo mass evolution, right? But instead of searching a small area, we need to search a huge area to find these galaxies because they're actually at redshift 7, they're 7 to 8, they're quite rare. So just for a comparison, what kind of area we've searched so far with James Webb, the largest, the Cosmos Webb survey was the largest area JWST survey executed so far, and it's centered on the cosmos fields, but it's only like a small part of the entire search area that we looked for really bright galaxies. And we scanned these galaxies for the cool gas lines, C+, emergence from both neutral and molecular gas. And because we scanned all the data that wasn't, it's next to the line, allowed us to also constrain some of the dust continuum. Oh yeah, first I want to say that, this was a cycle 7 program. And even though, the main program is completed, we still have a lot of efforts going on to follow up, first of all, do high resolution follow up of the C+, of the cold gas, spectroscopy with JWST, upcoming GRISM observations to understand the environment of these galaxies with JWST. So it's still, it's one of these surveys that keeps on, even though the main survey is gone, the sample keeps on being reused for all these new programs, and it's still very much, the collaboration is still very much alive. So we were able to observe the first statistical sample of dust detections in galaxies from redshift 6.5 to redshift 8, roughly. And the brightness of these dust detections at some point, for many of them, were kind of surprising, and it was difficult to understand how you make that dust. So let's talk a bit about sources of dust production. How do you make dust? So this is from a nice figure from the review by Snyder and Mylino. So they simulated a burst of star formation at redshift 20, and then look at, as a function of stellar mass, what is the amount of dust mass that you can produce with one stellar population. So often in the local universe, a lot of dust is thought to be produced by JWST, asymptotic giant branch stars, AGB stars. But these stars, they're relatively low mass, so it takes a while for the most massive AGB stars have a main sequence lifetime of 50 megayears at least, and some a few hundreds megayears. And so a lot of dust gets produced on sort of longer time scale, more than 1 billion years even. And so, yeah, there's a reasonable amount of dust that forms, but not that quickly. And they have other sources of dust, such as supergiants, but they're more, they don't produce as much in the most models. Most models will rate stars also produce dust very rapidly, but also don't produce a lot of dust. And then supernovae are thought to be a potential source of a lot of dust, but that's only when we consider, all the dust that supernova can make. There's also the reverse shock from supernova, and that reduces the total amount of dust that can survive. And so from this figure, you can see that, up to sort of a ratio of -3, so, the stellar mass being 1,000 times more massive than the dust mass, we might be able to understand dust formation just from sources of, stars, various stars. But if we go above that -3, we really start to struggle to understand what produces that dust. And so, of course, the Rebels galaxies turned out to be above this sort of -3 ratio of dust mass to stellar mass. Initially, this is an old figure before JWST. Some of these galaxies were truly extremely high in their dust mass compared to their stellar mass, but better stellar masses are now available with JWST, and so they've sort of moved a little bit into a more reasonable regime. Also, the error bars that you see here have all shrunk as the stellar masses were some of the biggest uncertainties here. So we're sort of convinced now that the typical Rebels dust-detected galaxy is about half a dex above this sort of -3 line, which is, where stellar sources really can't be the only method of dust production. So you need other ways of forming the dust, and a way to do that is through growth in the ISM. But you need to do that at a very rapid rate. So on the background, you sort of see this blue region, which indicates a model, a semi-elliptic model. So it gives sort of reasonable star formation history, so you can trace how much supernova and AGB can realistically form, how much dust they can form. And then on top of that, you need, for this sort of fiducial model, the bottom line, which is below the Rebels detections, you need a dust growth on the time scale of 30 megayears, so doubling time on every 30 megayears. But then where you sort of the higher up, sort of where the Rebels galaxies are, you need a much more rapid ISM dust growth model, which has a doubling time on scales of less than 1 megayear. So that's really extreme. And it's really, obviously in a semi-elliptic model, you can just put that in, like this is how fast you grow the dust. But, physically, can you really, form dust grains that quickly, or grow them that quickly? So ALMA obviously isn't the only way we can look at dust and dust formation. JWST also has a very interesting insight into this. With JWST, we see the rest-frame UV and optical, so we can have an idea of the attenuation curve of galaxies. And one feature that's very iconic is the 2175 angstrom bump. It's called a bump because in the extinction curve here on the right, you see a very clear bump feature. But of course, when we observe it in galaxies, we observe it as a dip, as an broad absorption feature in the rest frame UV spectrum, right? And it was first observed already in the 60s. And it's broadly thought to be due to PAHs or maybe other very small carbonaceous grains. We searched with my former PhD student, former postdoc in Cambridge, who's now moved on to Don in Copenhagen. But we searched the first galaxies that we got in from the Hubble Ultra Deep Field, so the deepest observations, for evidence of the 2175 angstrom feature. And we found this really nice galaxy at redshift 6.8. It has a very convincing dip. And if we look at the strength of this bump feature, or this bump amplitude, it's difficult to directly compare it to the Milky Way, as you don't know the AV of the galaxy. But if you take a range of realistic dust extinctions and compare it to a Milky Way curve, you see that this galaxy, which is the previous most distant bump detection was somewhere at redshift 2 to 3, and this is really a lot higher. It's just about consistent with a Milky Way extinction curve, right? Which is already very evolved. And it's very, it was already very difficult to explain some of these ALMA dust masses, but it's even more difficult to explain these features thought to come from PAH. And so why is that? So if you look at dust formation, this is again from a review by Snyder and Maialino. If you look at the star, so as a function of the initial mass of the star, how much dust the star can make, this is mainly AGB stars. And it's mainly the low mass stars that form the carbonaceous dust, whereas more massive stars that have a shorter main sequence lifetime make silicate dust. So PAHs are first and foremost an indication that there's carbonaceous dust. So you have even longer timescales, 300 mega years, before a star even moves off, a star that can form carbonaceous dust, even moves off the main sequence and can start forming these kind of particles. Moreover, PAHs are very volatile, so they're very easily destroyed in supernova shocks. So of all the dust grains that are most difficult to form in the early universe on a very short time scale, PAHs are the most difficult to form. It's very difficult to form by either supernova or AGB stars. And indeed, we published this in Nature, and it was a very nice theoretical article that came out in News and Views alongside it that sort of tried to explain what in their view was the only way to form these kind of cyclic grains. So, most often it's thought to be PAHs to form the 2175 angstrom feature, but it could also be graphite, very small graphite, cyclic particles. Either way, you need to form these particles in a sort of top-down scenario. So you either start with large graphite grains or large amorphous carbon grains, and these grains smash into each other and become more smaller grains, and eventually can make these tiny little carbonaceous nanoparticles. And so, yeah, potentially that could be a way of making these PAHs or graphites. And this way of making dust grains also links in with this with a recent theory of how to produce these big dust masses. So there's a sort of I like this model. It was developed by Narayanan et al. And it sort of connects these dust masses that we see with ALMA and these bump features. So I'll talk you through it. So you have some initial dust grains. So these big dust grains might survive the made by supernovas on relatively short time scale, and they'd survive the reverse shock. And you need to smash them together. And one of the things that's particularly important is if this happens a lot, this smashing process is when the ISM is very turbulent, which can be due to feedback from, so you need very bursty star formation that gives a lot of feedback, a lot of turbulence in this, allows bigger dust grains to smash into each other. And once you have these smaller dust grains, each of these smaller dust grains can very efficiently get metals from the ISM and grow bigger and bigger because they attract the metals on their dust mantles. Some part of these small dust grains, especially under the influence of UV radiation, will form PAHs. So in this model, the thing that really makes this sort of accelerated dust mass formation is that you really efficiently smash the large particles into small particles, because you have a small particle has a larger surface area for it to attract metals. So each of these small particles can become a large, bigger particle and really grow the dust mass. So sort of the key ingredient here, and so the prediction is that you would see this kind of effect mostly when there's very high specific star formation rates, which is generally true in the high redshift universe. But we can also look at it in galaxies and see how, for individual galaxies, what do their specific star formation rates look like. In order to do that, we need brighter galaxies to really study them in more detail. And so with my PhD students, Catherine Ormerod, we started looking in brighter galaxies, in this case in the NIRSPEC wide survey, for similar features. And we found this really nice galaxy at redshift 7.1 that again has very nice dip, but exactly at 2175 angstrom. And we actually find both from the photometry and from the spectroscopy, we find evidence for independently that it's fit much better with a bump feature. So, for example, a Milky Way dust curve. So, on the right panel, we see we allow the dust law to vary while we fit the spectrum and the photometry. And that while there's a broad range, you can see the green dashed line is the Milky Way attenuation curve, and it very much resembles something like that already. Whereas a Galaxies dust curve, which is down here, or an SMC dust curve, which is up here, are definitely significantly worse fit to this galaxy. So we can, because it's a bright galaxy, it was taking much shallower data. We can study the galaxy itself in a lot more detail. So we've done a nice analysis of the morphology, and what we see is that this galaxy sort of falls apart in sort of a main stellar component where the most of the luminosity is, and then there's sort of a long tail, which might indicate sort of like a merger scenario. And then if we, we forward bin the light and try to model the properties of the galaxies in these different bins, we can indeed see that the stellar mass is sort of focused towards the north of this galaxy. And if you look at the specific star formation rate, so where the bursty star formation is, that's more towards the south, towards this tail. So it suggests maybe like a merger-induced starburst in this particular galaxy. And we can then also try and model where the data really prefers to have this bump feature. And that is also located sort of in the south, so it seems to be a very localized signal and potentially linked to high specific star formation rates, such as been suggested in these models, that where these bump features are sort of it's a galaxy stage just before the dust can really grow a very large dust mass. So it's like the dust masses and the bump features are linked in that they're part of a larger process of building up the dust mass really rapidly. So it's nice, and it's the first time we've been able to sort of confirm that and maybe start to understand a little bit more of how dust can form in the early universe. Okay, so in my last 10 minutes, I want to focus a little bit on kinematics and also talk a bit more about turbulence in the ISM. It's important for many different things like star formation, but also, as we just discussed, how dust grows. So obviously in the local universe, we know that galaxies have this, follow this sort of tuning forks. We have really nice unbarred spirals and galaxies with bars in them. And you could ask the question, how early can features like this galaxy's bars, how early can they already start forming, right? So this is sort of the view, at least from the kinematics point of view, of how disks evolve as a function of cosmic time. So on the y-axis here, we have rotational support, so the circular velocity over the sigma, the turbulence in the system, as a function of redshift, right? And so for this studies, we sort of for the V over sigma rotational support of 1, it might be a marginally stable, just about rotationally dominated system. A sort of stable disk might have V over sigma of 3 or higher, maybe. And so you can see that obviously in the local universe, most star-forming galaxies are stable disks, where if we go already to redshift 2, most kinematic surveys seem to suggest that stable disks are more rare. And at best, star-forming galaxies are these sort of marginally stable disks. And the main reason for this is thought to be the increase in turbulence in the system. This makes sense. I talked early on how the specific gas accretion onto halos is much higher, therefore the specific star formation rates are much higher, and you expect as a result of that more turbulence in the ISM. Right, and so this makes galaxies in general less stable and less likely to be nice disks. However, some of the first JWST data has shown very surprising and different results, especially some of the earliest studies were imaging studies looking at the morphology, finding that some significant fraction of galaxies already look disky out to redshift 6 or higher even. And some nice studies with GRISM, for example, GRISM spectroscopy also have found nice velocity gradients suggesting these might already be disky galaxies. So why is there such a discrepancy between what was been found before, which was mainly based on ground-based spectroscopy, so using lines like H-alpha and O3? And one suggestion that my student, Sean Phillips, explored was using a set of simulations called the Ceres simulations, and looking at these galaxies in both the cold gas and the hot gas, like H-alpha. So JWST typically sees galaxies in H-alpha and O3, the hot gas, when it looks at the kinematics, and ALMA can see galaxies, in low redshift in CO, but at high redshift with C+ as the best cold gas tracer. Right. And here we see a galaxy that, from top to bottom, you see the flux, the velocity, and the velocity dispersion. The first panel is the cold gas disk, which looks nice and compact. And then when we look at H-alpha, we see that things like outflows start to become a much bigger part of the total radiation. So we see that the galaxy appears to be much more extended. We see that the velocity field starts to look very different due to the outflowing regions or the non-circular motion in this galaxy, and the dispersion is much higher. And then we can post-process these simulations and look at what, how, for example, a JWST near-spec mock observation would look like of these galaxies. And you can see that, the JWST observations arguably find it even harder to sort of see the morphology of the original gas disk, so the kinematic axis changes, and it becomes much more difficult to see the low dispersion in these galaxies. So we can model that, try to use the sort of state-of-the-art tools of how you would model these galaxies. So if you look at the high resolution, you can see, so this is what's called a PV diagram, so the velocity is a function of position along the kinematic axis. And here you can see the black lines are the models, the white lines are the data. You can see these outflows and how they affect the modeling in the PV diagram. Of course, at the low spectral resolution, relatively low, of JWST, of the IVU, we can't separate out very well what is outflows and what is the main galaxy. And that overall starts to means that you overestimate the typical turbulent motion by up to a factor of 5, as in this galaxy, and it underestimates the rotational support by a factor of 4. Right, so that's very significant, and it makes a difference between looking at a galaxy and thinking it's a marginally stable disk or a very stable disk. So that's extra motivation to really start using ALMA for these kind of studies. ALMA sees mainly the cold gas and substantially is less affected by things like outflows. I can actually understand the dynamics of the system a lot better. So one really nice galaxy was recently found by Lucy Rowland, a student at Leiden. there was a really nice ESO press release, this very pretty images was, I don't know, you might have seen it around. But what it shows is a galaxy that already seems to suggest that it's a very extended disk, as well as a very nice sort of barred structure. You can see the velocity field as well modeled by modeling here. But you can see that the bar structure in the center isn't that well reproduced by the model. And yet we see this bar both in the cold gas through C+, as well as from the dust. And the orientation and position of the bar, both in the dust and the gas, is exactly the same, suggesting it's a real feature. It's already like an extended disk with a bar-like structure, like you would see, I don't know, on the Hubble tuning fork that I showed. And this is at a redshift of 7.3. So it's really remarkable. It also has very high rotational support. If you look at typical cosmological simulations that try to reproduce the H-alpha kinematics, they predict sort of rotational support V over sigma of close to 1, and this galaxy is somewhere up at a V over sigma of 10 or so. So it's a really stable cold gas disk. And this is the modeling of the PV diagram. So again, velocity as a function of position. So it's a really nice example of how early really mature systems can already form. Obviously, we want a little bit of a larger sample. So this is what my PhD student, Sean Phillips, is working on. So she's starting to collect a larger sample from the Rebels survey with higher resolution C+ called gas kinematics. And we see, when we look at a larger sample, we see a lot more wide diversity of galaxies. So indeed, we find another nice stable disk, a number of marginally stable systems, still rotation dominated, but also quite a significant number of dispersion dominated galaxies, which really don't see, which have a very weak velocity gradient overall, almost negligible compared to their velocity dispersion. So we can have a look at, what does that mean? Is that, do we have just very turbulent systems here? So this is, again, a figure of the evolution of the sigma, the velocity dispersion, which indicates the level of turbulence in the system as a function of redshift. And interestingly enough, we actually see very small scatter in the sigma. So, this cold disk that I just showed, that's this galaxy here. The other sources are maybe a little bit higher in their turbulence or their velocity dispersion, but not much. So that's interesting. And especially when we look at the rotational support, there's again this really wide diversity. So we've seen anything from 10 to far below 1, so dispersion dominated systems. And these galaxies are selected to have very similar stellar masses, so all sort of around 10 to 9.5, 10 to the 10. So if their stellar masses are widely different, but their rotational support is, or their circular velocity is wildly different because their sigmas are very similar, it suggests that there's a wild variation in other baryonic mass components, so typically the gas mass. So it suggests that some of these galaxies are very gas poor, all of the mass is in the stellar mass, whereas others are maybe very gas rich, have a very large dynamical mass, very large circular velocity. Right? And this is not something necessarily that we've seen at lower redshifts. And it could mean that there's just more stochasticity, that there's more feedback that drives out a lot of the gas mass. And this is something that has been shown in various ways with JWST as well, that there's evidence for very strongly stochastic star formation history. And this could link into that and be a different way of looking at that. For our sample, we see at least one galaxy where we see sort of, direct evidence for that kind of scenario, where we see that a lot of the C+ gas actually is at very high velocities. We see this very nice broad component, very narrow central component. And both the red and the blue components of this system seem to sort of be significantly extended beyond where the main galaxy is, almost as a bimodal outflow. And the outflow rates as well of this galaxy, where it's sort of a lower limit that we can put on the gas mass that's outflowing. is significantly higher than what's been seen so far, at least at these stellar masses. And also what's significantly higher than some models predict. So this could be an indication of, sort of the same thing, that maybe some of these galaxies are very gas rich, very gas poor, and you see the imprint of that in the kinematics that they show. And yeah, this can teach us about how these galaxies are forming, how they're building up their mass, and maybe also telling us a little bit about why some already look very very mature in their dynamics. Okay, so just a little summary. I showed some ALMA and JWST studies that reveal the early maturity or accelerated galaxy evolution in the first billion years. And I looked at 3 topics: sort of ultraluminous galaxies above redshift 10, specifically how we can already start to derive the gas phase oxygen abundances of these systems, which are higher than we can currently explain with galaxy formation models. And then the early rapid buildup of the dust. Now we can look both at in absorption and in emission, both the dust mass and the tiny PAH particles that these galaxies seem to have in abundance, and how the strong implications that has for how rapidly dust must grow in the ISM. And then finally looked at identification of the first cold gas disk at redshift 7, but also the diversity of the rotational supports and the implications that has for how galaxies grow. So, thank you, and I'll take questions.
Do we have questions from the audience or from Zoom? Can you check Zoom? Thaisa? Maybe come closer.
Hi, this is Thaisa Stork-Bergman. Thank you very much for your presentation. I have a question regarding the most distant galaxy, Z14.
Yes.
You showed the spectrum, and you said, if I understood correctly, that there was no star formation. And for me, this looks so much like a starburst, very blue into the I suppose rest frame UV, I suppose, right? So I think it's quite blue. So I do see evidence for star formation.
Yeah, sorry, I should have been more specific. I was thinking about the kind of maybe exotic star formation scenario that you could come up with for GNZ11, where in order to get these kind of bright lines, specifically, for example, the nitrogen enhancement, maybe you're forming really massive globular clusters or other star clusters, and that explains the extreme brightness. In this case, sort of the lack of really bright emission lines, including something like carbon-3, it sort of gives you, there has been star formation, but you can sort of give an age, and it's just a little bit older, a few tens of mega years, you know what I mean? And so it doesn't quite explain in the same way, that this galaxy is so bright, because it's just you just happen to see it when it's right then when it's forming its most massive star clusters. Does that make sense? So it's a subtle argument. There is star formation. All of these galaxies are forming stars, but is it bursty enough that we can explain that it's so bright? That is sort of the question here.
Yeah, I understood that, for example, this one doesn't have gas, right? Because you don't see any emission. So it looks like it's already aged a little bit, but or maybe you consumed the gas or something.
Yeah, it's not, yeah, exactly. The sort of lines that you see, for example, the H alpha equivalent with it drops up very rapidly after a few mega years even, you know what I mean? And so you can sort of rule out that it's, I don't know, maybe in that recent 10 mega years since there was a burst of star formation. And so, yeah, so the star formation has to be a bit more continuous, but that makes it harder. Again, that makes it harder to explain the brightness. But even I have to emphasize, even with something like GNZ11, maybe you can explain it with a weird burst, but there's still no explanation of why these things are not happening at redshift 8, say, right? Why did they suddenly appear at redshift above redshift 10? Like, why? Like, it doesn't make any sense.
Okay, thank you.
Rogério, come close to 5.
Hello. So thanks for the very nice talk. My question is related to the dust formation in the very early universe. If you would play a little bit with the IMF, would you not change it enough to be able to produce like dust, like in this picture, changing the IMF?
Yeah, that's a good question. Potential. Yeah, I actually don't know. I've seen some discussion on it. You can tilt it a little bit, but we need to go almost to minus 2.5, if that makes sense. You need quite a significant amount of IMF variation, but maybe that's what we need at these very high redshift, right? To explain the brightnesses. So they're not completely unrelated. Yeah, potentially. It doesn't explain, for example, the absorption feature, the 2175 angstrom feature. Because that, the PAHs are very volatile. They're most easily be destroyed. But yeah, potentially if you form a lot of initial dust with supernova, and then in a top-down scenario, you could potentially form a lot of PAHs too in a turbulent medium. Yeah. Yes.
More questions from the students? Did anyone write in the Google Doc? Do you have questions from Zoom? Okay, so I have a question. I'm gonna push up here regarding the. How did you derive the star formation in that detailed study of the merger-induced starburst? How did you fit the stellar population, or how did you do this in more detail?
How do you do this one?
Yes.
Yes, so it is SED modeling. We use the photometry because we don't have IVU spectroscopy. We asked for it, obviously, but so we are now looking at a sample of galaxies where we do have the IVU spectroscopy as well. But here the only thing we had was the photometry integrated. We see that there's it prefers a bump even with the photometry alone. So yeah, so the SED fitting, the specific star formation rate, for example, it's quite strongly affected by the rest frame optical emission lines. Like oxygen 3 falls in one of the medium bands of NIRCam, so it's NIRCam imaging, and then we do the SED fitting. So it's really specific star formation rate is really on short time scale. It's really like burstiness almost, rather than sort of. Yeah, the star formation is more dominated by the emission lines than by the UV, if that makes sense.
I have one more question related to the first question from Thaisa. Can you show the plot with all the very far away first galaxies?
The first galaxies. Yeah.
So first a curiosity. So GNZ11 is because it was with Gemini North, is that right? And then GS?
Yeah, Goods North, yeah.
North, okay. Goods North.
So,
because then I just a naive curiosity. So you mentioned that why don't we see more weird cases in redshift 8? Isn't it
or
because
lower.
how many do we have there actually?
It depends a bit on how many of these photometric points you believe, right? So it's interesting that you don't see them at redshift photometrically selected. You don't see anything above this line, and then suddenly around redshift 10 or something, they start to appear above the line, and a number of them have now been spectroscopically confirmed, if that makes sense. So that
these are all the ones that in red that have been spectroscopically confirmed ever. So there aren't that many.
Yeah.
Like
yeah, so that's this, yeah, these fields, and then
in these fields.
no,
Okay.
yeah, it is, yeah, no, it isn't that many yet. So it's more, clearly evidence need to build up more. It's more, there's been a lot of these fields, but also in other fields, where you see similar photometrically selected galaxies that still need spectroscopic follow-up. And so far the spectroscopic follow-up has been quite successful. So yeah, definitely we need larger numbers, and I'm sure they will follow to sort of firm up exactly what is happening here, that you sort of, the only statistical power here is really in photometric candidates. But the fact that you have, when we saw these, we weren't necessarily sure that this bright galaxy was going to be real, right? So for all these photometric candidates, we were like, maybe this one was going to be real, but this one was quite a surprise. It just seemed too bright, but then, it in a way it's brighter than GNZ11 if you follow the halo mass evolution, if that makes sense. I mean, GNZ11 is brighter in absolute terms, but yeah, it really
And-
pushes. Yeah.
The last one, if nobody has any others. I'm very curious, just to try to understand why, like the morphology difference, or if there is any studies already of GNZ11 compared to JWST Z14. Are they different?
Yeah. So there's a foreground neighbor here, sort of. So you need to ignore that. But here's the surface brightness from GNZ11 in orange and GHC2 in green, and then this one in blue. So this is sort of the best morphology study there has been done so far. So there's differences there, for sure. So the other two are both N emitters and enhanced galaxies, if that makes sense. And this galaxy, isn't in the same way like a strong emission line galaxy with these kind of nitrogen lines.
And is there any way to know the environment, like is GNZ11 and GSZ14, are they in different environments, or because why would one have signatures of massive globular clusters forming? And
Yeah, you mean like large scale environments? Is there evidence for an overdensity?
yes, yes.
Yeah, so far not yet. So, for example, these two, they're a little bit apart, but that means they're not in the same. I forgot what the actual physical distance is, but they're too far apart already. I think one is just below redshift 14 and one above 14. That it's not even in a same cluster, whatever, protoclusters, you know what I mean? It's really large fields in overdensity. So I guess we don't have enough spectroscopy yet, but there's nothing GNZ11 similarly bright that's been confirmed. Nothing at exactly that redshift so far, but yeah, again, we don't have amazing tools for this except for very, searching for similar galaxies and then slowly spectroscopically confirming them. But yeah, not yet.
Okay. So thanks a lot for this very elucidating talk, and let's thank Renske again.
Thank you.
Thanks a lot. Bye.
Bye.
Let's see. Oh, no.